And the case study for today is forecasting the unemployment rate. But before we do that, we need to just look at the seasonal adjustments again. Because how could you make this seasonally adjusted time series? What you could do is to take a simple moving average of the 4 quarters of the year. Okay, so we can do that. Let's say that we are trying to make the seasonally adjusted price for Q3. Okay, for one of the Q3s here. Okay, for example, this one. Okay, then you would use let's see here, the values in front of this Q3 and the behind this Q3. So you would use values in the past and in the future of this Q3 to make the season adjustment. Okay, so for example, you would take Q4 and you would, which is in the future, and you would take Q2, which is in the past, and you have to also get an estimate of the first quarter. So would you use the quarter in the next year, because this is, or maybe I should do this. These are in 2009, and these values would be 2010. So would you use the first quarter in 2009, or would you use the first quarter in 2010? Well, what you can do is to keep both, but you add half of the Q1 in 2010 and you add half the Q1 in 2009. And then you could just divide by 1, 2, 3, half plus half is 1 by 4. And then you would actually get the seasonally adjusted value for Q3 in 2009. Seasonally adjusted value for Q3 in 2009. So that's how you could have a smoothing function which uses future and past information to make deseasonalized time series. Okay, so now let's get on to forecasting the unemployment rate. And the unemployment rate is the percentage of the labor force which is does not have employment but is seeking employment. Okay, so it's actually one of the most watched macroeconomic variables out there. And the reason is that if the unemployment rate is high, there will be greater demand for government services like Social Security, and the government would then have to maybe adjust some of the tax or legal framework to make sure that more people would find employment. And businesses are also quite interested in the unemployment rate, because if the unemployment rate is decreasing, then managers worry that there will be pressure to raise wages, because if the unemployment rate is low, then businesses, they have a hard time finding people they want to hire. Okay, so there will be a pressure on the wages, and this is often plotted as the Phillips curves. The Phillips curve. So this has inflation on the y-axis, and it has unemployment on the x-axis, and you have this downward sloping relationship, whereas if unemployment is high, then inflation is low, and if unemployment is low, then inflation is high. Okay, so let's say you're an economist at Bank of Norway, and your job is to develop statistical models for the unemployment rate. Okay, so the data we have is monthly data on the seasonally adjusted unemployment rate. So seasonally adjustment have been done for you. Okay, so you have unemployment rate from 2009 month 1. It's January. Okay, until 2019 month 9, September. So this is observation 1, and this is observation 129. Okay, so the data is compiled by OECD, and you can download the data if you want to. Fred has the Federal Bank of St. Louis has a lot of macroeconomic data if you want to look for some data, and it's free of charge. So you want to build a model to make a forecast and prediction interval. So that's like a point forecast. And so you want to make a forecast and prediction interval, okay, for the next month's unemployment rate, so 1 month ahead. So to get a forecast, we need a regression model for time series. So if we get a regression model for the time series, we get y hat, and we can just expand that regression model or regression line such that we get the point forecast. And by looking at the residuals around this fitted line, we can get kind of how do you say it? An idea of the dispersion around this forecast. That's what I was supposed to say. Okay, so you have the data, you have a month, and you have the unemployment rate, and this t variable, it's just counting 1, 2, 3, 4, 5, 6, 7, okay, and onwards until 129, and this is just made such in Stata by generate t, and the value of t is just a counter. Okay, so it's just counting from data point 1 until the last data point. So now we have kind of a numerical measure of time. So it's the number of months. So what we always do is that we plot the data. Okay, so the way we generate this is to just write in stata two-way, and we just say connected, and the variables. Unemployment rate, and we have t. No, we don't use the t here. We use the months. Yeah. Okay. So, and this will give you this plot, and you see that there's not much linearity going on, but you have these troughs and peaks of the data. So what can we do with this? We can use a regression model to generate forecasts of the time series data, and in this chapter or in this lecture, we are going to use two types of explanatory variables, the x variables, that we can use to model the unemployment rate over time. So the first one is the time index. And you should really not use this, and we are going to show you why. The reason why it's quite nice to know about this polynomial trend is to show you that it provides a very good fit of the process as long as you include enough powers of the time variable. But we will show you why that's not a very good idea. And the second one is a very robust, let's write that correctly, that's a very robust method. It's autoregressive models. And this is widely used in forecasting. And whereas this polynomial trend, it has pitfalls. So what we require as the assumptions is the same as the ordinary multiple regression model, and you know this. So one important one is that the errors are independent, but we will see that you can't really rely on the Durbin-Watson statistic to check for the independence of errors if you have an autoregression. So the autoregression uses lags of y. Oops. Uses lags of y, whereas the polynomial trend uses powers of time as x. Okay. So now we have we are going to use the first one. We are going to look at polynomial trends, and for example, we use powers of t, our t variable, the counting variable, remember, as explanatory variables. So for example, you have the date variable, you have the t variable, and then you make, let's see here, we can do this, and you make t squared, and you make t cubed, and so on. And here you have the unemployment rate in percentages. Okay, so this is your data. So for example, t is just the counting variable that we made some slides ago, and t squared is just t squared, right? So this is 1, this is 4, this is 9, okay? And t cubed is just, well, t cubed. So 1 to the power of 3 is 1, 2 to the power of 3 is 8, and 3 to the power of 3 is just 27, and so on. Okay, and the unemployment rate and the date is as always from the table. Okay, but here we have created 2 new variables. So now we can estimate or define the unemployment rate as an intercept. So this is the population regression, and you have the intercept and the slopes for these time variables. Okay, so what we are trying to do is to explain the unemployment rate only by using different powers of time, okay, plus the error, of course. So but note that we can also have powers higher than 3. For example, 6-degree polynomial, well, that would be defined as unemployment rate at time t equals the intercept times the first, or t to the power of 1, plus beta 2 t squared plus beta 3 t cubed plus beta 4 t to the power of 4 plus beta 5 times t to the power of 5 plus, and then we get to our t to the power of 6 plus the error term at time t. Okay, so you can make not infinite of these powers of time, but you could, if your data set is not very long, make quite a bit of these. So the more powers you include, the better you can capture some curvature in the data. So for example, t can capture like a straight line, right? And t squared can capture either this convex pattern or this concave pattern, and t cubed can capture this sigmoid pattern, so, like such. Okay, and a fourth degree polynomial can capture even more curvature. So let's see how we can make a linear fit of the unemployment rate. So the regression, the population regression is just unemployment rate at time t equals the intercept plus beta 1 times t. So that's the only power of t that we include in the model, and as we saw in the last slide, this can capture a linear trend. Okay, so the way we generate this plot is just to write two-way, and then we have connected, and we have the unemployment rate, and we have the date, that's in order to make this blue line and the data dots. But we also add the line here, and we don't need a separate regression for this. It's easier to just write a line fit, and not employment rate, but unemployment and date, like such. So now you can see that with a linear model, you are actually getting a pattern in your residuals, because negative residuals will follow negative residuals, and positive residuals will follow positive residuals. So basically, you can quite easily see that you don't capture the non-linearity of the data. So what you can do, or what we have discussed already, the simple regression of unemployment rate on t without polynomial terms does not give us a good fit. So we can try even more or a higher degree polynomial, okay, of time. So let's see. Let's say we try this 5 degree polynomial, okay, and what we do is that this, if we write this in Stata, then we generate, it's the same as writing generate t to the or t2, for example, because we already have the variable t, the counting variable, in our data set, and we generate a new variable called t2, and the value of t2 equals t to the power of 2. Okay, and we do such for the 4 variables that we need, And the last one is T5, which gets the value t to the power of 5. Okay, so now we have all the time variables in our data that we need to run the regression. So we run the regression here, and we are regressing the unemployment rate on t squared, t to the power of 3, t to the power of 4, and t to the power of 5. So, and what kind of results do we get? Well, we get an r squared of 91%, almost 91%, which tells us that this regression, by using these powers of time, will enable us to explain almost 91% of the variation or the variance in the unemployment rate. And we see that the p-value for the f, or the p-value for the f test is very close to 0, which means that we explain a significant amount of the variation in the data. And because we pass the f test, we can look at the coefficient and the t test, the p-value, or the confidence interval for the individual coefficients, and we see here that basically all the p-values for the t-test are very close to 0, which means that the probability of getting this coefficient, or something more extreme, something further away from 0, is basically 0, very close to 0. Okay, and what we see here is that we have an intercept of 2.2, and then we have these coefficients, but it's very difficult to interpret these coefficients, because they are really just coefficients based on our definition of time. Okay, but you see here that, well, this is negative 1.1 times 10 to the power of negative 6, which means that you have 1.1 times 10 to the power of negative 6, and this is equal to 0.000. Let's see, we have to move the point here 6 digits, okay, like so. 1, 2, 3, 4, 5. Okay, I forgot. So this is a really small number. Okay, but we are still using it because the p-value means that this is significantly different from 0. Okay, it's statistically significantly different from 0. And you see that because you have this really large t-value, and this comes about because the standard error of this estimate is even smaller than this coefficient value. Okay, so how can we use this? Well, if you look here, you have the unemployment rate, it's explained by this population regression with a 5-degree polynomial regression. And here you can run the regression, and then you can write predict y hat, okay, to make another another variable in your data, which is the predicted values, and the y hat is the red line. Let's see. So the red line here is the y hat, and you can see that by including more powers of time in like a higher polynomial regression, then you can explain these peaks and troughs in the data quite accurately. So this you would create by writing let's say two-way, and then you would have connected, and the unemployment rate and month, and then you would just add the line of y hat and month. Okay, so you see that you can explain a lot of the pattern in the data. So how can we use the polynomial trends? Well, we can try to use them to make forecasts using the regression, okay, the estimated regression. So we are using the 5th degree polynomial trend model, and what is the forecast and prediction interval for the unemployment rate in November 2019? So 2019, that would be period number 131, because if you remember, we had some data. Let's see here. We had some data, and 2009 month 1, it's observation 1 until 2019 month 9. That's observation 129. So, for example, here we have number 129. That's 2019 month 9, and the t variable is also 129, and I don't know what the unemployment rate was, but you see that the last data point we have is number 129. That's September, so we have to move 2 months in addition until period number 131 to get an estimate for November, which is month 11. Okay, so what we do is that we just say that, well, this is equal to t, right? 131. Okay, so and we know how to do this, because then we, let's see, unemployment rate hat is equal to let's see, and we take the intercept from this table. We have the intercept. Sorry, we have the intercept, and we have the coefficients on each and every one of these polynomial time variables, which gives us the regression line. Let's see, I have notes here on the screen. 26, 5, 5, 5, 8, lots of digits, plus 0.10, 84, 6, let's see, 3 times t. That's the first time variable, capturing the linearity, and this was minus 0.006 105 times t squared plus 0.000 1275 times t to the power of 3 plus 1.10 times the power of 10 to the negative 6 times t to the 4 plus 3.31 times 10 to the power of negative 9 times t to the power of 5. So these last coefficients, they are extremely low in absolute value. Okay, so when you plug in 131 for t, then you get that the unemployment rate for 2019 month 11 is equal to 2.09%. So that's your estimate, your point estimate of the unemployment rate in 2 months' time, if you use the polynomial trend model. Okay, so I told you that there are some problems with polynomial trends, and that's because you have to be cautious when you use polynomial trends to forecast time series, and because polynomials just extrapolate past trends, and they lead to poor forecasts when trends change direction. And how many powers of time should you include in the model? Your forecast will be very dependent on how many powers you include. So remember that we included the power of 5, or a fifth degree polynomial in our modeling. What if we included a sixth degree polynomial? Then our forecast would probably be very different, especially if you look far into the future. So and forecasting with polynomial is useful only if the patterns persist into the future. So there is really no theoretical reason why that should be the case. So, and polynomials with high powers of time can be very unreliable. So we managed to fit make a very good fit of the past data, but what we say is that it's overfitting, because you have a good fit of data, but you have poor forecasts. And how can we say that this is not a very good model for forecasting? Well, if you plug in higher values of t in your model to make a forecast longer into the future, then you would, by using our model, you would get this forecast that unemployment rate should just shoot up in the air here. So and what's the rationale behind this? It's probably a result of overfitting. And if you had used like the power of time to the power of 6, then maybe you would have gotten this really steep drop as a forecast. So to use the powers of t in a model, then you would have to be very careful. Often you should not go beyond at least power of 3 or power of 2. So just be very careful. So for the next video, we're looking into autoregressions.